So this is a presentation of how high-tech processes can be combined with more low-tech natural systems to obtain very high removal rates for all the key parameters in wastewater. This little article was written with two of my former students. You can look at why we do this in the introduction, but let's move on to, so here also in this presentation, we combine modeling and real data. So the modeling part is essentially based on the activated sludge model built by Guyer et al., same people who made our AquaSim. So they're strong modelers at the Swiss Water Institute. You probably recognize the reaction rates with ammonia going to nitrate. We have denitrification, nitrate going to nitrogen gas with organic matter. We have heterotrophs just growing aerobically. And then we have death and inactivation for autotrophic and heterotrophic organisms. And we end up with these expressions for the differential equations for the reactions that are the key reactions. Of course, like in ADM1, there are many other reactions involved, but these are those we need to just investigate the process. We can then go on to look at starting kind of at the end. Typically, the natural treatment is a constructed wetland. And here also we need some type of model. This is much less sophisticated. It's just an empirical model. And it's most of it is done by these Canadians. And so the reference here, if you want to follow that, you can go deeper into it. But essentially what it says is that if you know what kind of concentration you have coming in and you know what you need going out, you can estimate the area of your constructed wetland based on these coefficients. And we'll look a little bit closer what these coefficients can be. But you see, it's a much simpler than for the activated sludge model. If we move on, okay, and then there is some temperature compensation you can add. Yes, you can just read more about this. The typically required, recommended coefficients at 20 degrees for BOD, suspended solids, nitrogen, phosphorus, and fecal coliform removal are given in this table. We're not going into that yet, but then if we look at how high-tech and low-tech can be combined, it will typically, the main step will look like this. You have some pre-treatment, you have some bioreactors with sedimentation, sometimes integrated, sometimes separate. You take out some sludge, but then the special thing here is that the final step is some natural treatment, such as a constructed wetland. And you can achieve a lot by doing that. So this is quite popular, especially for smaller treatment plants where the discharge limits are low, so you need high quality water coming out. Often, and generally the best solution is that this is infiltrated into the ground, which is sometimes done simply by having a open bottom in the constructed wetland so it can percolate into the ground. And then, of course, we need some type of, in the advance, we need monitoring control, while the natural system generally just controls itself. The sludge taken out needs to go through some treatment, such as anaerobic digestion, to recover energy, get out nutrients, and maybe some soil components or something else. But as we know, nutrients, especially phosphorus and energy recovery, is the most important part. In the case that I'm using here as a example, the pre-treatment is a traditional septic tank. The bioreactor is a biofilm, moving bed biofilm reactor with sedimentation. And I'll come back to how we construct the wetland. And we're not, in this case, going into sludge treatment. It's just removed and taken to some centralized treatment. So if we look a little bit closer at these cases, 6 treatment plants that we constructed many years ago near Stavanger as a part of a national program for how to treat wastewater when you're far away from public sewers. Here we see some of the typical values for the 6 plants, P1 to 6, flow rate from 1 cubic meter, most of them around 1 cubic meter per day, which means typically somewhere around 10 people connected. So a farm, maybe with some people there working in addition, and in a couple of these cases also wash water from milking equipment on a dairy farm. And here you see the concentrations and all that, but we just move on quickly. You can read the details later. Now these are the results. We have, for case or A, is removal in kind of what call it the advanced part, the bioreactor and sedimentation, while part B is the total removal when we also include the wetland. And the reason for showing those separately is we can learn a bit about how these combine very well. If we look at BOD, for instance, most of it is removed in the first stages, especially in case 3 and 4. And we grouped plants 1 and 2 because they had very similar conditions, 3 and 4, and 5 and 6. So we see that when we go from just for BOD removal, there isn't that much gain by adding the wetland. While we see the case with the lowest treatment in the reactors, it reached almost the same total removal once we added the wetland. The main difference where we see the largest effect of adding the wetland is in phosphorus, where we, in the best case for the bioreactor, reached 39% removal, while after adding the wetland, we reached 86%. In the case where we had 36, we reached 96, and the lowest was 9. And in the case with the least in the reactors, we still got 90% in the total. And we know that phosphorus removal is a fairly complicated process, whether it's done biologically or with chemical means. So then in small scale, you don't have the equipment or the people to run it, but by adding the passive wetland, we still can achieve very high phosphorus removal. So these techniques are especially suitable for small scale treatment. And here we just look at the wetland itself separately. And we don't need to go through that now, but so let's just move on to pre-treatment, a little bit about that, a little discussion about options. Then about the bioreactors, saying there are just so many ways you can do it. We did a fairly simple biofilm method. Again, biofilms are easy to handle, so they're quite suitable, especially when you don't have plant operators that can follow up, like you do need when you have activated sludge, for instance. And the sludge treatment, we're not going into here. The constructed wetland, let's talk a little bit more about how that was done. And this is a drawing of a typical constructed wetland. And in these cases, we always use what is called subsurface flow wetland. Some wetlands, you just let the water flow on top, and they can be very efficient, but when there is a risk of spreading germs, spreading disease, you don't want that, because there can be kids getting in here or animals drinking and then spreading disease. But as long as you let the water from the advanced treatment upstream go below the surface in the root zone of plants, you avoid that problem. And by the time you get to the outlet, very little pathogens left. Still can be some though, so it's not you should like you can just dump it anywhere, but infiltration into the ground is certainly the safest in terms of that. All right, so let's scroll on a little bit. Here we have percent removal for the different parameters based on what the model says for natural treatment systems, the wetlands. The simple equations we saw above. So as an example, let's say your requirement is nitrogen removal. And let's say the government says you need 70% nitrogen removal, then given the flow here, we can go up to the line for nitrogen removal and we go over here and we get about 500 square meters. Now, if you want only suspended solids removal, you need very little area. If you get BOD removal, not much area. But if you want phosphorus removal, you need the most. So typically then, if phosphorus requirement is there, you can ignore the others. They will always be covered if you remove phosphorus properly. Now then, if we go back to the high-tech part, the process control, we have in these cases tried to achieve nitrification and denitrification in one chamber. Like we tried when you were doing your modeling for nitrification, we had this aeration on-off. Well, we used that in these small plants, so that way we achieved nitrification. And there are also some references to people who have published this kind of work. So in other words, in the bioreactor, we have oxygen increasing when the aeration is on, decreasing when it's off, and typically we have good nitrification when oxygen level is high, and low nitrification when oxygen is low, and then instead we have denitrification. So this is an efficient way to obtain nitrification and denitrification in a single stage. And here's a little bit about how it can be controlled, but we've talked about that before. We can also define aeration cycle as the period from when each time aeration starts. We could have every time it stopped, but let's just use that definition. And then we can talk about aeration fraction being how much of AC is actually air on. So in this case, air is on this long, and the total is that one. So in this case, the aeration fraction is probably about 1/3, a little bit more than 1/3, right? Roughly. So that, just keep that in mind when we move and look at some of the simulations. So here we have simulated the removal for different aeration cycles. So we have aeration cycle here, and we have aeration fraction here. And what we see is that if we have a very low aeration fraction, we say 0.1, and aeration cycle of 100 minutes, we get only about 20% nitrogen removal because there is not enough oxygen for nitrification. So if we increase aeration, we keep increasing the aeration fraction, and we increase the removal of nitrogen. And we see that in this area here, we can actually have 80% nitrogen removal with only taking the air on and off. Okay, this is based on lots of, pre-knowledge of the concentrations and volumes and everything, but we see that in this case, aeration on-off, 100-minute aeration cycle, and about 35 to 40% of the time is when the air is on, we get 80% removal. And then if we increase the aeration further, more aeration fraction, we get less and less nitrogen removal again, because we never get low enough oxygen level for efficient denitrification. Right? But also notice something that surprised us is that if we go very short aeration cycles, let's say 20 minutes, then we can also get 80% removal, but with a lower aeration fraction. So that will be more efficient, will save energy, because low aeration fraction means less aeration. So I think the best is frequently turning the air on and off in the right range can give very high nitrogen removal and a very efficient process. Now this is just over here is an example of a case where there is so high load that we don't get very good nitrogen removal. It's just only a 3-hour retention time. It's just not good enough. But with 6-hour hydraulic retention time, which we always had in these reactors, we can have very high nitrogen removal, as we also saw from some of the results. Now here comes some graphs just illustrating what's going on. The rates, like rate of nitrite production. So here the air is on, so we're producing nitrate, then air is off, and we're consuming it during denitrification. So you can study that a little bit closer, and we see that when nitrate is produced, ammonia is removed. But what we also see here is kind of the explanation why it's very useful to have really short aeration cycles. For instance, here, oxygen goes to 0, and it remains there for a while before air is turned back on. And during this period, we would think maybe that we have efficient denitrification. But not really. We see here, nitrate removal has stopped because there simply isn't more nitrate there to be removed. So in essence, some of these periods when we have long cycles is just waste of time. That's why keeping very short cycles is the most efficient. Now then, I think this part is also something that if anything, you should read this part, efficiency, because this summarizes some of the basic idea that I've been trying to bring across throughout the semester is, now what do we mean by efficiency? It doesn't mean maximum removal. It means high removal with low energy consumption and so on. So um, here, just going through 3, 4 different criterions for um, how to evaluate whether a process is efficient or not. And I think that is important. I feel it's not often enough um, considered. So you should read that. The rest is more technical, but that part is very general and relevant for the whole course in many ways. Now then, a little bit about the wetlands, how they perform, phosphorus removal. Um, it says in the literature that it's really dependent on the loading rate, and it certainly is. But what we also see from previous publications is that they say you should not go higher loading rate than something down here. And we have tested here much higher loading rates. And the main reason why we could do that is because we have the advanced treatment in advance, so that we remove most of the BOD. So the wetland is not very good for BOD removal. The BOD removal is much better to do somewhere where you can supply oxygen on demand. The wetland does not do that. So if you remove the organics and also a large part of the nitrogen before the wetland, it becomes much more efficient at removing phosphorus. You don't fill up all the space in the soil with biofilms growing on organics. So that way the phosphorus can much more easily penetrate to sand, for instance, and get immobilized there, just absorbed. So that's the main reason why these cases work so much better. So what it really means is that if you used a standard wetland design, which is just taking septic tank and then a wetland, while we put the bioreactor in between. That way you can shrink your wetland by maybe 90%. And that can make it possible to build many places. For instance, in these cases we look at here, they were just like in the backyard, under the lawn of the house on these farms. Doesn't take up much space at all. And it seems more stable. So that was, I think, the most important part. It's a little bit about the removal and the area, how we calculated it, nitrogen, more confusing data and not so important because a lot of it was removed previously. And also in the cases where almost all of it was removed before the wetland, of course, the removal there was quite low. A little bit about these coefficients, how they would be can be modified somewhat depending on temperature to calculate the area required to treat the wastewater. So then in the end, just kind of summarizing about sustainability. Sustainable treatment is what we aim for, really, always. And this seems like a easy, low-cost way of treating wastewater in rural areas. Urban areas, you have pipelines and everything. Rural areas, this could be a very nice way to do it. I'm sure there are variations of this, and this is a long time ago we did this, so I'm sure it can be improved, but in principle, it is quite good, and it turned out to be fairly cheap. So we calculated and published some results in a Norwegian journal where we demonstrated that if the distance to the nearest sewer is more than 100 meters, this is cheaper and safer way of doing it. And 100 meters is not very much. So if your house farm is 100 meters from the pipeline, I'm sure the local government will force you to connect. But for the farmer himself, it would actually be economically favorable to just treat it on the farm. And definitely if you live a few kilometers away, and many Norwegian farms come in that category. So therefore, such fairly high-tech, still not very advanced, but fairly high-tech bioreactor treatment combined with wetland seems like a very feasible technique for small-scale wastewater treatment.